So for this part of lecture, we'll be discussing 4.4, coordinate and basis. So particularly, we'll be talking about coordinates in linear algebra. Okay, so first, what are the coordinate system in linear algebra? So when you studied your analytic geometry courses, sa JEP na Sec 4 or Sec 5, you were introduced to what we call the Euclidean Cartesian plane. Okay, the Euclidean rectangular coordinate system or the Cartesian plane. In that Cartesian plane, we are to assume that we have equal scaling and the axis, particularly the x-axis or the y-axis, they are perpendicular. So in this particular graph or figure here, figure A, the scaling is 1 to 1, meaning 1 unit of or 1 unit in x-axis is the same as the 1 unit in the y-axis, meaning the length of 1 unit in the x-axis is the same as the length in the 1 unit of y-axis. However, there are some cases where we cannot or we are allowed to use other scaling. So for example, here in figure B, our axis, x-axis and y-axis, they are still perpendicular. But notice that the length of 1 unit in the x-axis is not the same as the length of 1 unit in the y-axis. Okay? Or maybe we are also allowed to use this type of configuration wherein the axes are not actually perpendicular. Okay? So in here we have this x-axis, okay? And the y-axis is slanted. So the x-axis here is still horizontal, just like in the previous cases A and B, okay? But the y-axis is not vertical. So it is slanted. But in here, particularly in figure C, the 1 unit in the x-axis, the length of 1 unit in the x-axis is the same as the length of 1 unit in the y-axis. Okay? But on the fourth figure here, we can combine the configurations in B and C, meaning the axes are not perpendicular and also the scaling is not 1 to 1, meaning um, the 1 unit of on the x-axis is not the same as the 1 unit on the y-axis. Okay? So why do we introduce this kind of configurations for the coordinate system? Okay? In linear algebra, remember that we are talking about vectors. Okay? In the usual configuration, equal scales and perpendicular axes, this one here, you can think of this as the vector from the origin to 1 of on the x-axis, and this vector here is the vector from the origin to 1 of the y-axis. Okay? And we call this vector here as our I, and we call this vector here as our J in the two-dimensional coordinate system. Okay? In the usual two-dimensional coordinate system. But notice in here, this vector here is longer compared to this vector here. Okay? In the x-axis, we have this 1 unit. It is shorter than the 1 unit for the y-axis. And you cannot call this your j vector, or maybe you cannot call this your I vector. Okay? Unlike on the figure A. If you call this your I vector, since they are of equal scaling, you can call this your J vector. On the other hand, in here, the scaling may not be the same. Okay, in fact, the scaling here is not the same as this, and therefore possibly one of them cannot be your j vector or cannot be your I vector as usual in A. And for this configuration C and D, definitely you will see that this is not the same as your j vector because your j vector is assumed to be um, perpendicular to your I vector. Okay, but these two vectors are no longer perpendicular. Okay, and etc. Okay, so the question is, how do we construct such configurations in linear coordinate system in linear algebra? Okay, of course, we will apply what we have learned in the previous lessons. Okay, so we have a vector space. Before we begin all those things, let us define what we call or what we say to be a finite dimensional vector space. So, a vector space V is said to be finite dimensional, okay, if V can be spanned by a finite numbers of vectors in V. Okay, meaning you can get all the vectors that can span, okay, that can span V, and if possible, if you get a finite number of vectors only that can span V, okay, meaning that can generate all the vectors in V, okay, then we say that V is finite dimensional. Okay, if we cannot find a finite number of vectors that can span V, we say that V is infinite dimensional. Okay, remember the word span, it means a linear combination. Okay, so meaning you can find a finite number of vectors in V whose linear combination can generate or whose linear combinations can generate all the vectors in V. So, for example, the vector space R3 is finite dimensional. Okay, the vector space Pn of polynomials in the variable x of at most degree n is also finite dimensional. Okay, so and however, the vector space of functions, okay, the vector space of functions is not finite dimensional. So this is actually infinite dimensional, meaning we will not be able to find a finite number of functions, okay, a finite number of functions that can generate your space of functions. Okay, to understand this better, in the vector space R3, okay, you can get the span of the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, if you get the span of this, you will get the space R3. So these three vectors, okay, these three vectors is enough to generate all of the elements in the vector space R3. So the span of this is equal to R3. The second item here, if you look at the span of your set 1, x, x squared until your x to the n, if you get the span of this, you will get your Pn of x. Okay? So to show this, let me just give this part here. The span of your 1 x until you have x to the n, okay? These are all polynomials. So a sub 0 plus a sub 1x plus until you have a sub n x to the n. Okay? Such that your a1 or a0, a1, etc. until an are scalars. That's your span. Okay? But the space of scalars, okay? Our scalars are actually real numbers only. Real numbers. Which means this is a polynomial. Okay? This is a polynomial of utmost degree n. Okay? If an equals 0, then your polynomial is degree n minus 1. It's still a polynomial of utmost degree n. And this is precisely your Pn. This is precisely your Pn in the variable x. So the span of this is equal to this. Okay? So that's your span in number 2. Okay? For the first item, okay, let me just show how we do this span in the first item. Over here. So if we get any vector in R3, a vector in R3 is represented by ABC. ABC. This is an element of R3. Okay? And as I have said, that this guy here, the span of 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? This is R3, meaning we should be able to write this vector ABC as a linear combination of this. And ABC is any number or any vector in R3, okay? But this vector ABC is simply A times 1, 0, 0 plus B 0, 1, 0 plus C 0, 0, 1. So meaning, whatever numbers you use A, B, and C as an element of R3, you can always write it as a linear combination of these three vectors. So we have found a finite number of vectors. In fact, there are only 3 of them here. At the very least, 3 of them, okay, that can span R3. So R3 is finite dimensional. Okay, R3 is finite dimensional. So in this lecture, in fact, in this course, we will be talking mostly of finite dimensional vector spaces. In fact, in here, the only infinite dimensional vector space that we have talked about is the space of functions. The only infinite dimensional vector space that we are going to talk about is the vector space of functions. And if I am recalling it correctly, there are no other functions. There are no other infinite dimensional, there are no other infinite dimensional vector space except for this function that we are going to talk about in this course. A lot of them, most of them, if not all, most of them will be finite dimensional. Okay? So, let us now go to what we call a basis. Let S be the set of V1, V2 until Vn. Okay? Let this set be a set of vectors in the vector space V. Okay? Then we will call S a basis for V. Okay? A basis for V if first S spans V. Okay? And second, S is linearly independent. In the span, we have talked about this. So this means condition 1, span of S must be equal to the vector space V. We talked about span in the second lecture, 4.2, okay, as a subspace of a vector space V. But span can generate all of the vectors, possibly, okay? So that is the first condition. And the second condition is that the elements V1, V2 until Vn is linearly independent. Okay? The set S is linearly independent. And remember, we just talked about linearly independent sets. Okay? So no vector in S can be written as a linear combination. So no vector in S can be expressed as a linear combination. Linear combination of other vectors. So that is linearly independent. Okay? And we have a theorem. And we have a theorem regarding that. Okay? So S linearly independent. Okay? If and only if K1, V1 plus until Kn, Vn equals 0 implies K1 equals 0, K2 equals 0 until Kn equals 0. Okay? So most of the time, we'll be using this theorem to show the second condition. To show the first condition, okay, we may use this method here, at least in R3 or in Rn. In the space of polynomials, we use the method that we did as in before, like compare coefficients, etc. Okay, so span and linearly independent for to define a basis. Okay, so example, this set ij, this is a basis for R2. Okay, this is a basis for R2. So they are linearly independent. Remember, let me write I. This is the vector 1, 0. And j, this is the vector 0, 1. So you can easily show that they are linearly independent. Okay? Any scalar multiple of I will only produce 0 in the second component. Oops, sorry, the j is wrong here. It should be 0, 1. So again, any scalar multiple of I will only produce 0 in the second component, but j has 1 in the second component. So they cannot be linear combination or scalar multiples of each other. Okay? And does it span V? Does this set span V? Thing is, yes, just like the way we did in this example. You have AB, then your AB, the vector AB can be written as AI plus BJ. Okay? So this set is a basis for V. In Rn, remember your E1, E2, E3 until En. Okay, let me just write that Ek. So Ek, this is what? 0, dot, 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 0, 1, okay? 0, dot, 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 0. And this here is the kth component or kth entry. So 0 everywhere except for one component, and that should be found on your kth entry. So E1, you have 1 here and then 0 everywhere else. E2 will be 0, 1, and then 0 everywhere else, etc. En will be 0 everywhere else except on the last entry, which is 1. So that's your Ek. Okay? And this set, E1, E2 until En, okay, this is also a basis for your Rn. Okay? For Pn, okay, here, for Pn, 1x, x squared until xn, this is also a basis for Pn. So we have shown that this set spans this vector space because every element of your Pn is just a linear combination of all of this. And in the previous lecture, we said that this is a linearly independent set. Okay, so this is also a basis for your for the Pn. Okay, we call this the standard basis. This one is the standard basis for R2. This one is the standard basis for Rn. And this one is the standard basis for Pn. Okay? So question is, are there non-standard bases? Okay? And probably the more important question is this basis unique? Okay? The answer to that question is no. There can be many bases for a vector space. Okay? There can be many bases for a vector space. And therefore, those other bases, okay? For example, ij is the standard basis for R2. For if you found another basis for R2, it's not the standard basis. Okay? E1, E2 until En is a standard basis for Rn. If you found another basis for Rn, that's not the standard basis. But they are still basis. Okay? They are still basis. And similarly for your this. This is a basis for Pn, the standard basis for Pn. If you found another basis, then that basis is non-standard basis. Okay? And we will be talking about a lot of times. We'll be talking about non-standard basis. Okay? So for example, show that this set here, 1, 0, 0, 1, 1, 0, 1, 1, 1, show that this is a basis for R3. Okay? This is not standard. Let me write the standard basis for R3. The standard basis for R3, standard basis for R3, using the previous slide. Standard basis for R3, it's your I, 1, 0, 0, J, 0, 1, 0, and then K, 0, 0, 1. IJK, or sometimes this is your E1, E2, and E3. So this is the standard basis for R3. Now we will show that these three vectors here as a set forms a basis for R3. So what do we need to show? Again, two things we need to show. Let me label this set as S. Okay? Two things that we need to show. Span of S must be equal to R3. And then the second thing is S linearly independent. These are the two things that we need to show. So to show, okay, solution. Let's do number one, span of S. So to show that the span, okay, that the span of S equals R3, we get any arbitrary elements of R3. Okay, we get any arbitrary elements of R3 and we write it as a linear combination of the three vectors. Okay, so for this guy here, by the way, for this guy, you have two things to show. Span of S, this is a subset of R3. And the other case, R3 must be a subset of span of S. That is what we mean by equality of set. Span of S, subset of R3, and R3 subset of S. Okay? Now, this condition here is always true. Always true. By definition, because this contains three vectors, or the vectors here are have three components, right? So the span of this will also have three components. Each element of the span of this, okay, must have three components, and therefore they are elements of R3. So this one is always true. Okay, so we are left to do this. R3 must be a subset of span S. Okay, let me write this subset. So this is what we're going to do. Okay, and to do that, you start. Let get any arbitrary vector in R3. Let A, B, C, okay, be an element of R3. Okay, we want to find that this ABC can be generated by these three vectors here. We need to find coefficients for this vector, and this vector to obtain that ABC. Okay? So how do we do that? So here, A, B, C, we need to find K1, 1, 0, 0, plus K2, 1, 1, 0, plus K3, 1, 1, 1. We need to find the exact values of K1, K2, and K3 to obtain ABC. Take note that your ABC here are actual numbers in R3. K1, K2, and K3, you need to find them. What are these K1, K2, and K3? Okay? But just like before, you can write this as a system. Okay? you can write this as a system. So let me write on the left-hand side these guys here, and on the right-hand side, this guy here. Okay? Particularly, if we compare the first components, you have K1 plus K2 plus K3. The first component will be A. So K1 plus K2 plus K3, that's your first component A. For the second component, K1 times 0, so that's 0. But you have K2 here plus K3 here. And then the second component on the right, on this side here, is equal to B. And lastly, for the third component, this is 0, this is 0, and this is 1. So you have K3 equals C. And voila, here you have K3 equals C. So your K3, the coefficient K3 must be the same as that third component. Okay? And this implies what? So these two equations implies, or these two equations imply that K2 plus K3, but K3 is equal to C. Yeah, K3 equals C. So K3, which is equal to C, must be equal to B. And therefore, your K2 equals B minus C. Okay? And then if we combine now this equation in the first equation, okay? First equation, you have K1 plus K2 plus K3 equals A. But you know your K2. K2, it's B minus C. And you know your K3. K3 is equal to C. So you will have K2, or sorry, K1 plus your K2, it's B minus C. That's your K2 plus your K3, it's C. And then is equal to A. Okay? And notice, you can simplify this. Minus C plus C, that will cancel out. This tells us that your K1 must be equal to A minus B. So what does this mean? What does this mean? This means that the vector ABC, this can be written in terms of these three vectors, 1, 0, 0, 1, 1, 0, 1, 1, 1. This can be written as A minus B, 1, 0, 0, plus K2, it's B minus C, B minus C, and then 1, 1, 0. And then finally, C, 1, 1, 1. Okay? So meaning, if you get any vector in R3, use this formula, okay? Then you have a linear combination using the vectors 1, 0, 0, 1, 1, 1, 1, 1, 0, and 1, 1, 1. Okay? So meaning, since we have found actual values for K1, K2, and K3 that will satisfy the equation, it means that R3 is a subset of the span of S. Okay? And therefore, span of S equals R3. So, span of S equals R3. So, we have shown this first part. Okay? Okay? Question? For this part here, by the way, for this part here, give me a vector, any vector in R3. Just tell me any vector. Anyone? Okay, let me check that chat room. So 3, 4, 5. So we say, so 3, 4, 5, 3, 4, 5. So this is a vector in R3. So this vector, according to this, okay, we should be able to write this as a linear combination of these three vectors, 1, 0, 0, 1, 1, 0, and 1, 1, 1. And according to this one can be written as, so A minus B, so 3 minus 4, that's negative 1, 1, 1, 0, plus you have B minus C, so B minus C, 4 minus 5, again that's negative 1, 1, 1, 0. Sorry, in the first vector here, it's 1, 0, 0. Okay, the second vector is 1, 1, 0. And then finally, the third vector, it's C. So we just take the third component here. So plus 5, 1, 1, 1. So you have your 1, 1, 1. Okay, so if you combine this, you will get this vector. So that's what it means to have this linear combination. Okay, so whatever vector you have, whatever vector you use this formula and you will get those case, the actual values for case. Okay, now that's for the first part, span S equals RT. The second part, linearly independent. And remember, all we need to do, if we assume K1 F1 plus, or K1 V1 plus K2 V2 plus K3 V3 equals 0, we have to find actual numbers for the K, okay? And we want to show that those actual numbers are 0. But we can use this. We can use this. Okay? So suppose so this is for number 2. Take note. Linearly independent. Suppose K1 1 0 0 plus K2 1 1 0 plus K3 1 1 1 equals the 0 vector. Okay? But so using the previous part, K1 or K3, it's your C, but C here is equal to 0. K2, okay, K2, it's your B minus C, so that's your 0 minus 0, and again 0. And K1, it's your A minus C, and it's still 0 minus 0. And that's it. It's easy, right? Because of that basis representation, or that linear combination representation. So A minus B, that's 0 because you have 0 plus 0 minus 0. B minus C, that's your 0 because you have 0 minus 0. And then C, your C is equal to 0. So this means that, S is linearly independent. And we have linear independence here on this part. We have equality of span here. So equality of span, okay? Linearly independent. We conclude that S, so thus S is a basis for R3. Okay? So a basis for R3. Question? So again, in order to find that a set is a basis, two steps. One step is linear independence. The other is that the span of your set must be equal to the vector space. Okay? Another example here. Show that 1 plus x, 1 plus x plus x squared is also a basis for P2.
Excuse me,
So,
sir?
yep.
Can you just go back for once? Thank you.
You're welcome. So, here, we want to show that this set here, let me label this as S. We want to show that this set here is a basis for the vector space P2. Okay? So first, we want to show that span of S equals your P2X. Okay? But again, the span is always a subset of the vector space, provided your set belongs to the vector, or provided that the vectors in your set are elements of your vector space. Okay? And then the second is S, excuse me, linearly in depth. Okay? So again, show two things that we need to show. Okay? So let me write here again. Excuse me. Let me write here again what P2X is. So the vector space will be, okay, so let me just write what the elements of P2X are. And these are of the form A0 plus A1 of x plus A2 of x squared. Sorry, A0 plus A1x plus A2x squared. And again, in here, A1 or A0, A1, and A2, these are all real numbers. Okay? These are the elements of your P2X. Okay? So this is your first vector 1, second vector 1 plus x, third vector is 1 plus x squared. Okay? So to show one solution, to show one, we get arbitrary elements. We get an arbitrary element of P2. So let A0 plus A1x plus A2x squared. This is an element of your P2x. Okay? And then we need to find scalars. K1, K2, and K3 so that the linear combination equals this one. Okay? So find K1, K2, K3 such that, let me write this on the left, such that K1 times 1 plus K2 times 1 plus X plus K3 1 plus X squared. So we want to find those scalars K1, K2, and K3 such that this left-hand side equals A0 plus A1X plus A2X squared. And again, A0, A1, A2, they are actual numbers. Okay, they are actual numbers. K1, K2, and K3, these are scalars that you need to find if you can. Okay, you need to find the values of K1, K2, and K3 if you can. A0, A1, A2, these are actual numbers. Okay, so remember how we did this last lecture? You look at the constant, you look at the coefficient of x and coefficient of x squared. So for the constant part on the left-hand side, you have, this is constant. So K1 times constant, it's just K1. And then here you have 1 plus x. So the constant part is 1 times K2. And here, this is the constant part times K3. So you have plus K3. And the constant part on the other side, it's A0. Okay? The x part, meaning the coefficients of x, this one doesn't have an x. Here we have an x, K2 times x. So the coefficient of that x there, it's K2. While here, the coefficient of K3, or the coefficient of x here, it's still 1 times K3. So this one is K3. And the coefficient of x here, it's A1. And finally, the coefficient of x squared, this doesn't have an x squared, this doesn't have an x squared, this has an x squared. Coefficient is 1 times K3. So you have your K3 equals A2. And notice, this is very much similar to the previous problem. You will be able to find your K3 immediately using the third. So K3 equals A2. Okay? So this implies that K3 equals, sorry, this is redundant, but let me write it anyway. So K3 equals A2. And then I use it in here, okay, to find that K2, this is equal to, so K2 plus K3, but K3 equals A2. So K2 plus A2 equals A1. So K2 equals A1 minus A2. Okay. So we now have an actual value for K2. For K1, we substitute it here. Okay, we substitute it here. So again, substitute it there. So your K1, let me write this completely. K1 plus K2, but K2 it's A1 minus A2 plus K3, but K3 equals A2, and this is equal to A sub 0, which means that K1, so A2 cancels out, K1 it's A0 minus A1. So actual numbers. Okay? So what does this mean? This means that your A0 plus A1x plus A2x squared, okay, can be written as, so A0 minus A1 times the vector 1 plus A1 minus A2 times the vector 1 plus x plus A2 times the vector 1 plus x squared. Okay? So meaning, whatever second degree polynomial you get, or at most second degree polynomial you get from P2, using this formula, okay, or using this formula here, you will be able to write it in terms of this. Okay? You will be able to write it in terms of this. Okay? E.g. So let us look at some examples again for this before I write the conclusion for this part. So example, suppose I want my x squared, so 3x squared minus 1. Okay? 3x squared minus 1. This is the same as your minus 1 plus 0 times x plus 3x squared. Right? This is your A0. This is your A1. This is your A2. So in terms of these three vectors here, 1, 1 plus x, 1 plus x squared, this 3 minus x squared, sorry, this 3x squared minus 1 can be written as what? So A0 minus A1. This is your A0. This is your A1. So A0 is minus 1. So we have minus 1 times 1 plus, for this part here, A1 minus A2. This is A1. This is A2. So A1 minus A2. So that will be negative 3, 1 plus x plus A2. And this is your A2. That's 3. So plus 3, 1 plus x squared. Okay? So this polynomial 3x squared minus 1 can be written as a linear combination of 1, 1 plus x, 1 plus x squared. And these are all the combination. Negative 1 times 1 plus 3 times 1 plus x. Sorry, negative 1 times 1 plus negative 3 times 1 plus x plus 3 times 1 plus x squared. Okay? But the conclusion from here, okay, the conclusion from here, this means that, so span of 1, 1 plus x, 1 plus x squared, this is equal to p to x. Okay? Okay? For linear independence, just like the previous solution, we use the zero polynomial. Okay? We use the zero polynomial. So we want to show now number 2. Let me erase this first part only. But I'll retain that these equations or this formula. Okay. So now, for the second part, we need to find linear independence. So we want to show linear independence. So suppose K1 1 plus K2 1 plus X plus K3 1 plus X squared equals the zero polynomial, which is 0 plus 0x plus 0x squared. Okay? This is the zero polynomial. But we will use this. So using the previous part, K1 will just be 0 minus 0 because K1 is A0 minus A1. This is your A0, this is your A1. So 0 minus 0 equals 0. K2 is also 0 minus 0 because you have A1 minus A2. This is A1, this is A2. So 0 minus 0 equals 0. And K3 is A2, but A2 is equal to 0. So therefore, S is linearly independent. So linearly independent, spanning is equal. Okay, this guy here. So we conclude that S is a basis. Okay, we conclude that S is a basis. Therefore, S is a basis. Okay? Basis for, let me complete this. Basis for P2X, since we are talking about the vector space P2X. Okay? So again, 2 steps to show that a set is a basis. Span must be equal to the vector space, and the set must be linearly independent. Okay? Question? Now, we began in talking about coordinates, rectangular coordinates and non-rectangular coordinates. So what is that in relation to what we just discussed? Coordinates relative to a basis. So suppose we get a basis for a vector space S, vector space V. So let S with basis V1, V2, and Vn. Okay, let S be a basis for a vector space V. Then every vector V in the vector space V can be expressed in this form in exactly one way. Okay, in exactly one way. So vector space V, okay, we get a vector bold V, and we can write V in terms of the basis elements. V1, V2, Vn. So C1, V1 plus C2, V2 until plus Cn, Vn. And this is the only way we can write it. I will not prove this in this class, okay? But believe that there are no other ways to write the vector as a linear combination of a given basis. Okay? Example, oh, I erased it here, but I had an example where I had an example from here that I think it was 3x squared minus 1. And I was able to write this as negative 1 times 1 plus, I think, negative 1 again, 1, negative 1 or negative 3, 1 plus x. Yeah, I think it's negative 3. And then plus 3 times 1 plus x squared. So this 3x squared minus 1 can only be written this way using these elements. 1, 1 plus x, 1 plus x squared. In Rn, say in R3, just like this, we use this vector 3, 4, 5. Okay? And this 3, 4, 5, using these elements 1, 0, 0, 1, 1, 0, 1, 1, 1, this is the only way that you can write 3, 4, 5. There are no other ways. Again, using these elements in the basis. Okay? If you get another vector, okay, you use this formula here. That's the only way you can write the vector using these basis elements. Okay? So that's what this theorem is telling us. You got a basis for the vector space. Okay? If you get a vector in your vector space, there's only one way to write it as a linear combination of your basis elements. No other way. Because there's only one way to write, okay? Because there's only one way to write any vector using the basis elements, we will collect these coefficients, C1, C2, Cn. Okay? And we will write them into a vector form. And that vector form will be called the coordinate. Okay? So, if S is a basis for the vector space V, and S has these elements, V1, V2 until Vn, and if we take a vector V, okay, in the vector space capital V, such that we found a linear combination, okay, we found a linear combination of the basis elements, then these scalars, C1, C2 until Cn, we call them the coordinates, okay, the coordinates of your vector V, okay, relative to the basis S. Take note of that, relative to the basis S. Okay, if you put these coefficients, C1, C2 until Cn, okay, into a single vector, okay, C1, C2 until Cn, so you write it as a single vector, then this vector is called the coordinate vector of V relative to S. And we denote this way. So parenthesis bold V with subscript S, meaning we are talking about the coordinates of V using the elements of S. Okay? Okay? So example. Suppose in R2, so example. In R2, okay, standard basis, we have seen standard basis. is 1, 0, and 0, 1. These are your I and j. So if you get an element in R2, AB, you can write this as A 1, 0 plus B 0, 1. Okay? Graphically, this is your standard Cartesian plane. This is 1, this is 1. Okay? This is 1, this is 1. If this is your point AB, okay, you will have this vector. This means that this guy here, this is your A, and this guy here, this is your B. Okay? So graphically, you have this. And this is your ij. So let me write this as a vector ij. So this is the vector I, this is the vector j. Okay? So ai plus bj. This is in R2. So what about if we consider another basis? Consider another basis. Let us go to R3. We have seen earlier 1, 0, 0, 1, 1, 0, 1, 1, 1. We have seen that this is a basis for R3. Okay? Particularly, if we get an element of R3, A, B, C, this can be written as, how can we write this? How can we write this? Using the formula that we had earlier. So 1, 0, 0 plus 1, 1, 0 plus, I know that the third you have your 1, 1, 1. For the second, you have B minus C. Yeah, it's B minus C, B minus C. And then for the first here, you have A minus B. Okay, if I remember, verify the formula, I think this is the formula. So A minus B plus B minus C plus C. Yeah, that will give you A here. And then in here, you have B minus C plus C. You will get your B. And this is your C. Okay? So this is the formula. We found that this is already a basis for R3, and this is the formula. So what? The vector 3, 1, 2. Okay? Let me emphasize that we found this from previous example. From previous example. Okay? And let me label this as your S. So from previous example, okay, 3, 1, 2, using this formula, we have A minus B. So 3 minus 1, that's 2. 1, 0, 0 plus B minus C. 1 minus 2, that's negative 1. 1, 1, 0 plus C here, it's just 2. 2 times 1, 1, 1. Okay? So what does this mean? The coordinates of your vector 3, 1, 2 relative to the basis S, this is equal to 2, negative 1, 2. So this is the coordinates of this vector 3, 1, 2 relative to the basis S. Okay? Using the standard basis. So using the standard basis, the standard basis for R3, okay, the coordinates of 3, 1, 2, sorry, 3, 1, 2, let me write standard basis. The coordinates of 3, 1, 2 using the standard basis is still 3, 1, 2 because that is our standard. This is our regular coordinate system. So standard basis 3, 1, 2 is still 3, 1, 2. But using a different basis, the coordinates of 3, 1, 2 using this basis S here, the coordinates become 2, 1, negative 1, positive 2. Okay? Question? Question? Now, we can also talk about coordinates in other vector spaces. Before, our coordinates, we are only restricted in R2, in R3, and now even in Rn. Okay? But we can extend that notion to other vector spaces. Okay? For example, this. We can try to graph the vector space P2. Okay? The vector space P2. We have shown earlier 1, 1 plus x, 1 plus x squared. We have shown that this is a basis for P2x. And let me rewrite what was the formula there. So from previous example, if you have a0 plus a1x plus a2 x squared, you can actually write this as a0 minus a1 times 1 plus a1 minus a2 1 plus x plus a2 1 plus x squared. Verify that this was the formula that we obtained earlier. Okay? Okay? So this one is a basis. We have seen that. Okay? This is our vector P. Okay, the vector P. So now, vector P, which is equal to negative 1 plus x squared. Using this formula, a0, it's negative 1, a1, there's no x part here. So we will get only negative 1 times 1 plus a1 minus a2. We don't have a1 again. a2 is positive 1. So we have negative 1 times 1 plus x. And then a2 here, it's positive 1 plus 1 times 1 plus x squared. Okay? So minus 1 plus x squared can be written as negative 1 times 1 plus negative 1 times 1 plus x plus 1 times 1 plus x squared. Okay? But what does this mean? What is the coordinate of the vector P? This means that, so the coordinate of the vector P relative to the basis S, let me again write this as our S, okay? Relative to the basis S, this is equal to -1, comma, -1, comma, +1. Okay? So coordinates relative to a basis. Of course, if you have the standard basis for your P2, the coordinates will just be the coefficients of your 1, x, and x squared. That becomes your coordinate in the standard basis. You have a different basis here, so the coordinates possibly is different. In fact, it is different here. Okay? Question. I think this will be my last example for this day. Yep. So here we have to show.
Sir?
Yep, sorry.
Please, could you go back to your previous slide, please?
Okay, wait. Yep, it's here.
Okay, thank you.
Yep, you're welcome. So for this problem, we'll do this completely. Show that S here, this is our S. Show that this is a basis for the vector space M22. So this is the vector space of 2 by 2 matrices. Okay? Then find the coordinate vector of this matrix relative to the basis S. Okay? Relative to the basis S. So let us do this completely. First, let us recall what is your M22. M2 by 2. The elements of this vector space are 2 by 2 matrices A, B, C, D, where, of course, your A, your B, your C, and D, the entries are just real numbers. Okay, this is your M22. We want to show that this is a basis. We want to show that this is a basis. Before I do that, let me tell you that the standard basis, what do you expect to be the standard basis of the matrix M22? The entries of the standard basis of M22 has 1 in one of the entries and 0 everywhere else. Okay? So you have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay? So that's the standard basis for M22. Here, this is not a standard basis. Okay? This is not a standard basis. But we will show that this is also a basis for this space. Two things to show, remember? First, span of S must be equal to M22. And second, S is linearly independent. Okay? And just like before, we always start with this part. We want to find span of S. Okay? We want to find the span of S. So solution. So for the first one, We get any arbitrary matrix. 2 by 2 matrix. A, B, C, D. Let this be an element of your M 2 by 2. So we need a representation for this matrix using the matrices here. Okay? So we need to find K1, K2, K3, K4 such that K1 1 0 0 0 plus K2 1 1 0 0 plus K3 1 0 1 1. Oh, sorry, this is 0 plus K4 1 0 0 1. And we want to show that this linear combination is A, B, C, D. I mean, we need to find the values of K1, K2, K3, and K4 such that this linear combination is the matrix ABCD. Okay? But as usual, we write this as a linear system. Okay? Look at the first entry here, A11. Okay? First entry, first entry, first entry, first entry, compare it to the first entry there. But we find that you have K1 plus K2 plus K3 plus K4. This is equal to A. The A12 entry, this guy here, K1 times 0, that's 0, K2 here, and then this one is 0, and then this one is 0. So we only have K2 equals B. For K3, for A21, this entry, this is 0, this is 0, this is 1, so you have your K3. And then this is 0, and this is C. For the A22 entry, this is 0 here, this is also 0 here, this is also 0 here, and this is 1 here, so times K4. You have K4 equals D. And we are lucky, at least in this example, because we have actual numbers for K2, K3, and K4. K2 equals B, K3 equals C, K4 equals D. For K1, you have K1 plus K2 plus K3 plus K4, but we all know K2, K3, and K4 already. Okay? So this implies our K1 has the value A minus B minus C minus D. Okay? Question? So meaning we have actual values for K1, K2, K3, and K4 if we get arbitrary values for ABCD. Okay? So here we have the value for K1, K4, K3, and K2. So span of S, this is equal to M2 by 2. Okay? Question? How about now, linear independence? Instead of ABCD, we want this to be 0. Agreed? So for number 2, so suppose To shorten up here, let me just label this as M1. So let me label this as M1 here. This is M2 here. This is M3 here and M4 here. Let me label those matrices M1, M2, M3, and M4. So suppose K1, M1 plus K2, M2 plus K3, M3 plus K4, M4 equals the zero matrix. 0, 0, 0, 0. This is your zero vector. So suppose it's the zero matrix. We want to solve for K1, K2, K3, and K4. But we can use this. So from the previous part, from the previous part, we have K1 equals 0, K2 equals 0, K3 equals 0, and K4 equals 0. Okay? Because K4 equals D, but D here is 0. K3 equals C, C here equals 0. K2 equals B, B equals 0. K1, it's A minus B minus C minus D. But A, B, C, and D, they are all 0. So we have this. Okay? Therefore, S is linearly independent. So S is linearly independent. Therefore, S is a basis. S is a basis for M to 2. Okay? Question so far? And that's the first part, you see? Show that S is a basis for the vector space M2. Second part, I want to find the coordinate vector of this matrix here relative to the basis S. So for the second part now, 1, 5, 2, 6. This can be written as a linear combination of, so we will try to find that 1, 0, 0, 0 plus 1, 1, 0, 0 plus 1, 0, 1, 0 plus 1, 0, 0, 1. Okay? But again, if we look at this solution here, K4, the coefficient for this, which is K4, is just simply the D. The coefficient of this, which is K3, is equal to C. Coefficient of this, which is K2, is equal to B. The coefficient of this, which is K1, is A minus B minus C minus D. Okay? Which means that in here, this is just 5. Here, 5. This is 2. This is 6. And this guy here, it's 1 minus 5 minus 2 minus 6. Okay? And that's equal to negative 12. Okay? Therefore, the coordinate vector, okay, of 1, 5, 2, 6 relative to the basis S, this is the vector negative 12, 5, 2, 6. And that completes the solution for this guy.